قدر مش أحد يصدر اسمي أمري وأحمد وقدرة من لساني يفقهوا قولي واجعلني وزيرا من أهلي هارون أخي أجد به أزري وأشكر في أمري كمصداق كثيرة ونذكر كثيرا منكم بنا بصيرا. So we continue what we talked about last time about Hertzian dipole. Okay, so we are assuming we have a dipole antenna, something like this. So two wires, two conductor. Okay, we have two conductor here connected to a feeding line, transmission line, which is coaxial line. So the inner conductor go to one wire, the outer conductor go to the other wire. This is called dipole antenna. So we have the antenna here along the z-axis, and we are assuming that this antenna is very small. Very small means the length is very small compared with lambda. This is the lambda of 50. The reason we are assuming it's very small to assume that the current distribution is uniform. So at each point here we have the same current, which is constant, IZ, like DC. So it's not DC, but because the length is very small, and if you take very small piece of this wire, the current can be assumed to be uniform. Then we have used Maxwell's equation for Faraday's law and Ampere's law to calculate the radiation from this dipole. So how much field will be going away from the dipole when R is the distance between the observation point, the point where I am calculating the field. It's very far. So when R is very big, the field E and H at this point are given by this equation. This is called the far field approximation. Far field means we are assuming R is very big. So what we have is only E theta and H phi. All other components are zero. E R, E phi, H theta and H R are zero. These are spherical coordinates. Then using these two equations, which are making sense. Last time we have made several observations about the field. The phase is changing by R, so we have like spherical phase. The field is inversely proportional to R, so the further the point, the less the field. The field E and H, both of them are dependent on the direction, which is what? And what is the direction control here? What information tell me about the directional properties? Sin theta, the only angle we have theta. Do we have phi here? Do we have phi? We don't have phi because the magnetic field is uniform along phi direction. So magnetic field and electric field are uniform, so we don't have phi here. The only directional dependence is sin theta. Sin theta is very important here. From the equation of the field, I can calculate the average power density. How can I calculate the average power density? S. What per square meter? How can I calculate it? E cross H conjugate, 1 over 2 real part E cross H conjugate. We have done this in all the course. The average power density. From S, I have managed to find a new parameter, very important, called normalized radiation intensity. The normalized radiation intensity is the ratio between S over S maximum. So after you calculate this guy, after you calculate 1 over 2 real part E cross H conjugate, then you will divide whatever you have here, S over S maximum, you will get the normalized radiation intensity, F. What is the maximum value of F? What should be maximum of F? 1. It's something over the maximum of this thing. So, by doing this calculation based on E and H, very easy, we have reached to the definition of the normalized radiation intensity equal to sin square theta. This parameter is very important because now I have the angular dependence or the directional properties of the radiated field. F is related to the average power density over the maximum, so we call it normalized. What can I do with this equation? And how useful is this equation? It's written here. How useful is this equation, Abdullah? Here. It will help us to sketch the radiation pattern. So from this equation, I can understand how the radiation of this antenna changes direction. If this is a transmitting antenna and I need to receive maximum power, should I place the receiver here or here or here or which place, which direction? This equation tells us. So if this is the radiating structure, where should I put the receiver? Where? Based on this equation, where should I put it? So like here? No. Like here. Yes. This will give you maximum radiation, or here, anyway, look, anywhere. As long as the angle between these two guys is 90 degrees, like this, you will receive maximum power. So here, here, all of them maximum power. If I put the receiver here, what is theta along this direction? You receive 0 because the angle theta is measured from z axis. So this is the very important, the most important parameter, as I told you last time, is the radiation pattern. So from this very equation, which is the normalized radiation intensity, I can now draw the radiation pattern, say in YZ plane. 2D, I will go with 2D. In YZ plane, what is the radiation pattern of this antenna? So along the z-axis, what is theta along the z? What is theta along the z-axis? If you don't use spherical coordinate, you will take 0 in this chapter, which might be 1/3 of the exam. 0. Okay? So along the z-axis, what is the angle theta here?
0.
0. So along the z-axis, what is the value of this guy?
0.
0. Then you will go here gradually. As you go gradually from theta equal to 0 to theta equal 90 degree, what should you draw here?
From 0 to 1.
You will draw something like this. You will have something like this. Okay? This is assuming we have here like 45 degree. So at 45 degree, what is the value of this guy? At 45 degree, what is the value of this? 1/2, right?
Yes.
So here we have 1/2. At 90 degree, what is the value of this function?
1.
1. So here we have 1 and 1.5. 50% 1. You can do it the way you like. Then you will continue until you reach to theta 180 degree. What should you draw here? Based on this equation?
0.
Something like this. We'll have something like this. What we are doing here is polar sketch. You know polar? Did you take polar sketch before?
Yes.
Polar means which course?
1 or 2.
Okay, so in polar coordinates, we are going with angle theta in like spherical shape or circular shape. On the other side, when theta go from 0 to 180 degree, on the other side, what should I see? Just sketch the equation, substitute. What should you see here?
The same thing.
So theta here is 90 degree. Again, theta is 90 degree here, by the way. So you will see the same thing. This is what you will see. This is the radiation. So if your antenna is here, maximum radiation is here. 0 radiation is here. In between, you have some radiation. Very simple. This is 2D radiation pattern in YZ plane. Agree? What about if I make this X? What should be the new sketch? Next Z plane?
The same.
The same. No change. It will be the same. If you go in, look, the angle phi is changing. Angle phi starts from X. So at X, phi is 0. Then at Y, phi is 90 degree. Then here, phi is 180. So in XZ plane, phi is 0. When we say XZ plane, means the phi is 0. Phi constant plane. At YZ plane, what's the angle of phi at YZ plane? What's the angle of phi? 90 degrees. So when phi is constant, when phi is constant, this is called elevation plane. So the elevation plane is the plane defined by the plane where phi is constant. We call it elevation plane. Okay? So what I did is the radiation pattern in the elevation plane. So for any angle phi is constant, and if you assume phi is 40 degrees in this plane here, what should be the radiation pattern? For any angle phi constant, what should be the radiation pattern? Should be different than what I did?
No.
It's the same. There is no phi here. So if you are in phi 0 plane, in XZ plane, or in phi 90 degree, YZ plane, or any constant phi, and you can have any constant phi, like phi 45 degree. Where is this plane? On phi is 45 degree. Some here, middle way between X and Y axis, vertical plane. You will see the same thing. You will always see the same. What about if I go in XY plane? Are you following with me, Shabab? And what I did here is that if you take this equation and sketch the equation, if you sketch this in YZ plane, this is what you will get. In XZ plane, this is what you will get. In any vertical plane where phi is constant, you will see the same thing. Right? What about if I go in XY plane? If I need to sketch this in XY plane, what should I see? So assuming this is like X, Y. Where is the dipole? Where is the antenna? The antenna was along Z. So the antenna is here. Okay? The antenna is here. Or the antenna is here and you need to sketch the pattern here in this plane. In XY plane. Okay? So the antenna is here and I need to sketch this in XY plane. What should I see?
Donut.
Not a donut.
What is angle theta in XY plane?
0.
90.
Angle theta is measured from z axis. Along z, theta is 0. In XY plane, any point in XY plane, theta is 90 degrees. Right? Agree? So in XY plane, how can I sketch this? How does it look like?
A circle.
Circle. Okay, it's a circulation. Well, theta is always 90 degrees. There is no other value. In XY plane, theta is constant. So this guy is 1. 1, anyway is 1. Non-directional. Okay? So now you have better visualization about how this antenna is radiated. This antenna, assuming this is the axis. So if your receiver here at any point in this plane, in XY plane, you receive the same power. So put the, as I told you, this is a transmitter, put the receiver here or here or here. As long as you are in this plane, you receive the same power. Once you go a little bit up or down, you receive less power. Okay? Here less power. Until you come here, you receive 0 power. This is radiation pattern. Okay? So we like to draw the radiation pattern either in 2D. What I did is 2D plot. This is any vertical plane, we call it elevation plane pattern. مستوى الرأس يعني. This is the مستوى الأفق XY plane. We call it azimuth plane. Azimuth means أفق. Okay? Azimuth plane. Elevation is a vertical plane. Any phi constant plane. يعني any plane like XZ, YZ or any vertical plane. هو XY plane is perpendicular to this plane. Okay يا شباب؟ This is 2D radiation pattern. What should be the 3D radiation pattern? What should be the 3D radiation? If you want to look at the radiation pattern as a 3-dimensional, مجسم. What should it look like?
Donut.
Huh?
Donut.
Like you know the apple, bring an apple and remove the middle part. It will be the 3D radiation pattern. تفاح, just remove the donut. You know the donut? It's donut radiation pattern. Okay, so in the center there's nothing. If you take cut here in this plane, what should you see? If you take a cut, you will see circle, non-directional. If you take a cut in any vertical plane, what will you see? And if you take a cut here or here or here, anywhere, you will see this. This is the radiation pattern of Hertzian dipole. Again, when you are designing an antenna, when you design an antenna like this, when the customer comes to you asking you to design an antenna, the first question, what kind of radiation pattern you need? يعني should the radiation be maximum, minimum, in what direction? Based on this information, you will design the antenna. What about if I make the antenna like this? Okay? Now what's the direction of maximum radiation? This transmitter, where should I put the receiver? Here?
No.
Here.
Yes.
This maximum radiation. Maximum radiation here, all the way here. Here you will receive 0 radiation. What about if it's like this? See, okay? Yes, sir.
دكتور بخصوص الرسم اللي قبل شوي لل 3D visualization ايوه هذه تعتبر بس ل differential point في الرود صح ولا؟
It is yes. يعني what we are doing here, we are assuming we took very small piece of this, lambda over 50, and then we sketch the radiation pattern. Later, inshallah, we will take the whole thing. It will have almost same radiation pattern. And even if you take the whole thing, lambda over 2. Lambda over 2 is the standard antenna. Standard antenna is lambda over 2. So if lambda is 30 centimeter, 1 gigahertz, this will be 15 centimeter. I think it is 15 centimeter, I think. Is it? It's 15 centimeter, I believe. Or more, no, I think it is more. Anyway, as you, this is lambda over 2, it will have a radiation pattern similar to this. A little bit different. Very similar to this. Okay? So, based on this information, the maximum is happening at theta equal to, what is the maximum here?
90 degrees.
Theta equal to 90 degrees. What you see here, ya shabab, is sine square theta. This sine square theta. If equal to sine square theta. So the maximum radiation is along the 90 degrees, along this direction. I want to make this equal to 0.5. I want to make f equal to 1 over 2, 50% power. You know half power point? I need to find the half. So when f is 1, this will give you maximum radiation. Okay? When f is 1 over 2, this will give you what? Half power. Half the power. What's the meaning of half power? 10 log 10 log ايه؟ 0.5 which equal to I'm 3 dB. We took this before, half power point. So the antenna is radiating maximum along this guy. What is the direction where we will have half power, half maximum power? What should be the direction? Take F and make it equal to 1 over 2. Yeah, take F. F is sin square theta, right? Make it equal 1 over 2. What should be theta? 45 and 135. Okay? This is the half power point. The points where the field will be half power. Because maximum is 90 degree. 1 over 2 will give you 45 and 35 degree, 135. This means along the direction of 45 degree, here yani, you will receive 50% of the power. If you have 10 watt here, you will receive 0.5 watt here. Along 45 degree and along 135 degree. The beam width between them, yani this range between these two angles is called what? What should we call this range? Again, this is direction يا شباب, that direction where the power radiated is half the maximum power. Agree? Now, the range between these two angles is called what? Give it a name. Half power beam width. Half power HB beta. It's half power beam width. This is a range of angles where the power is maximum or up to 0.5%. If you go further, you receive less than 50%. We are interested in the half power beam width, النطاق الترددي where the power is 50% or more, because this is assumed to be the good radiation of the antenna, يعني 50% and above. Okay? So what is the half power beam width for this case? What's the half power beam width? 135 minus 45. So what's the half power beam width here?
90.
So the half power means the radiated power is 50% from the maximum power. The half power beam width here equal to what? The big angle minus the small angle. The big angle minus the small angle. What is the big angle? 135. What is the small angle? 40. So the half power beam width is 90 degrees. How important is this? And why you need to know the half power beam width? If you need to have sharp radiation, should you increase this value or decrease this value? Yeah, the radiation we have here is like this. This is wide beam. In some application, you need the beam to be like this. Sharp beam. So the guys here will receive nothing. Okay? It is used in security. In military application, you need to send some information in a certain direction where all the other guys cannot receive it. The spies cannot take the signal. So you try to make the beam very sharp. So this guy must be reduced or increased? It must be reduced. So the lower this value, the sharper the antenna radiation. So the power will be focused only in a small range of angle, small direction. Okay, شباب? So it's very important to define the half power beam width. How can we find it? Very easy. Take F, which happens to be sin square theta. Happens here to be sin square theta. In some equation it will be sin theta plus cosine theta minus tan theta. It will be any function. Make it equal to 0.5. It will give you two angles. Subtract the bigger minus smaller, it will give you half power beam width. Does this make sense? Okay, شباب? This is what is the name of this plane? The vertical plane XZ or YZ elevation plane. What is the name of the XY plane? Azimuth plane. The antenna on your phone, guess what kind of radiation pattern it has? It has exactly this radiation pattern. Because you should be able to receive information anywhere at any direction. Okay? In some, this radiation pattern is called omnidirectional radiation pattern. Omnidirectional means it is non-directional in one plane and the direction in any other vertical plane. Yeah, this antenna here is non-directional in this plane. Look at this plane, non-directional, circle. And the direction in any other plane vertical to this plane. This is what we see here. This is antenna you have in your mobile phone or any personal communication device. Okay? Some other antennas like the dish in your house. You know the dish? Does it have this radiation pattern? No. This is because this radiation pattern has low gain. The gain of the antenna in your phone is 1 to 2 dB. Not that high. Because you can receive signal, usually You have to be closer to some base station to receive signal. If you go out in the desert, you receive nothing, right? Because you are away from base stations, the station you see above the high-rise towers. You are always in the city, so you will always receive signal. You don't need high-gain antenna. But you use the dish antenna to receive signal from satellites, from hundreds or thousands of kilometers away. So you need directive antenna. We don't have this kind of radiation pattern. We have directive radiation pattern, as we have seen last time. Anyway, this is the radiation pattern story. Now we go to the next part. بسم الله الرحمن الرحيم. قال سبحانك لا علم لنا إلا ما علمتنا إنك أنت العليم الحكيم. Can you stop?